Let's resume our second part. So, did you take some coffee? Yeah. So now let's talk about the second approach, which is not involved with any analytical optimization procedure inside of it. And also we are bypassing the concept of the distribution function. So let's go for this kind of approach, which is what is called by joint estimation and optimization. In other words, previously, our new spender has two parts. First, an estimation of demand D. And based on this estimation, my Q calculation is a separate part. So we've seen from our previous example that our demand estimation of mean and standard deviation, that doesn't mean that our order quantity matches the average or mean value of our estimated demand. So the second part of the inventory optimization has to be done in order to eventually determine the optimal order quantity that can minimize our expected total inventory cost. However, these days we are kind of trying to integrate these two different parts into one, and now we want to verify the data, or in other words, some of the observation into order quantity directly. So it's actually one by one pair, just because if we happen to decide one order quantity, we will see one realization of a total inventory cost. So let's assume that we have infinite amount of time, infinite opportunities to make any experiments. Then we can try first to 500 with a million of times. And then we see the average cost. We can try 1,000 million of time and see the average cost. By the way, this just sounds quite familiar to what you have already done in our, in our Excel file, just because this reminds you the approach that we have done here, right? So what did you do? You didn't use any of the optimization at all. We just derive the total inventory cost of two different combination of demand and order quantity. And then you just take the average of all the different demand realization in this case. So if you have millions of such sales data, you kind of can do some experiments for all different number of the order quantity, and then eventually you will get what are the best or the optimal order quantity that you want to have. So the beauty of it is you don't need to know the distribution function. You don't need to even take any extra step to understand the G function at all. So you don't have to, in other words, what I'm saying is we are still using the G function in some sense, but we are not taking the derivative, which is the quite hard part. And we are not using any integration function at all, expectation. Instead, we are just taking the average. So here in this simple approach, maybe if we have a lot of observations of demand, we could have easily know the optimal order quantity. However, we have to repeat those number of experiments each time, or we have to have this kind of the table. So for this kind of simple environment, we actually don't need to implement any of the fancy method. Just the simple averaging would suffice for us to obtain the optimal order quantity as 2,500 here. For a more complex cases, then we have to resort another technique that is called by disjoint, what is it, optimization technique. And let's talk about the good thing about this. So here, the traditional approach, we have demand estimation and the inventory calculation as a separate part. So if we happen to have some error here in our demand estimation, those errors are coming forward to my inventory optimization. So even if I did the correct calculation of F inverse of something, if I happen to have some errors in my F estimation, then those errors are coming out, and sometimes those errors are magnified in my F inverse calculation because my F inverse is quite sensitive to F function. And because of that, even a small error here can make a huge difference in my optimal order quantity calculation. So maybe as an alternative, what do we have? We have a reinforcement learning framework, and this is quite suited to our objective. So we want to know the action, the best action that can minimize our inventory. So we can try a lot of experiments, and then we can obtain the best decision that for their problem. And for those kind of problem, this kind of reinforcement learning is the optimal. And probably it's good to know the difference between machine learning and reinforcement learning. Do you see the essential difference between the two? So what I meant by machine learning is machine learning, image recognition or classification, and so on. So for all those applications, image recognition or classification, for all these techniques, there's no action in it. However, in the reinforcement learning technique, we have some actions in it. So what are the examples of these actions? In this AlphaGo example, we are playing Go, Baduk, and what are the actions in this problem? Each play, position, each. So each action is one of the squares here, and then you need to place your stone, white stone, black stone, in one of the empty spaces around here. So you have a certain number of actions to take. And what is your objective? Your action should have an objective because you need to verify whether your action is good or bad. So essential objective of this game is to win the game. So simply, I know that I have to choose my action to win. But this is not simple. Why is it challenging? So let's not talk about the case of having so many places to put my stone. This is one big challenge, obviously. But the other challenge comes from the other player, yes. And also, what's the meaning of the winning? Winning the game, does it come right after placing one stone? No, it takes a lot of actions in order to eventually know whether I win the game or lose the game. So here, the decision is quite complex because by just taking one stone, the impact of one stone can be quite big or small, but regardless of those impacts, I don't know exactly what is going to happen to my winning or losing, which comes quite a lot of periods later than my current period. So the time lag here is quite challenging part of this reinforcement learning for playing this Go. Because of that, people say that this kind of game be, I mean, the people can never apply any learning or automized machine-based playing that are playing better than the human. Do you remember when this game was done in 2016? How many years ago? Exactly 10 years ago. So just 10 years ago, we didn't know whether the machine can do better than people. Nowadays, nobody is thinking that we are doing better than the machine, right? So the challenge has been resolved by this Google's DeepMind, but at that time, it was resolved eventually, but the way they solve it is very expensive because they need to do a lot of simulation basically. So for example, if I take my stone here, I need to do a lot of simulation to see the impact of the winning or losing. So they are basically just running the game to the end and then just to see whether I win the game or lose the game. So how do they do that? They just remember a lot of previously the game history, and then they can simulate what's going on in the future. So they are using machine learning, obviously, because they need to remember the patterns from the history of those play. And then, but eventually, what they want to find out is the optimal action, where to put in order to eventually increase the probability of winning that are estimated today or right now. So what they have done is in order to do a lot of simulation, they implemented what is something called by distributed computing, right? So this kind of calculation is too complex, so no single machine can do it within several seconds or several hours. So in that case, it takes much longer time to implement the best action set. So because of that, they've implemented a lot of different number of hardware at the same time. It was quite expensive. Even today's standard, these kind of hardwares are quite expensive, but it's one way magnitude higher than expensive than today's measure or 10 years ago. And we know that there are two different methods like supervised learning or unsupervised learning. But for our reinforcement learning technique, we can implement both ones. So in other words, supervised learning is something that we know from history or previous history of game. So they are referring to a lot of previous games to see what was the best action. Unsupervised learning is something that we are doing right now. So for this current positions of all the stones, which was not there before, then I want to find out the best solution by implementing new actions here and there and here and there, and then see the probability of winning, how this changes. So AlphaGo is not just successful for the complex Go game. It can do a lot of different simple games that we have played when I was very young, before you guys were born, right? So many years ago, I was playing these games, and let's see if this can 여기다가 안 되네. 비디오? 안 되네. 이거를 띄울 수가 없나? 클릭을 하면 돼? 안 되는데. 원래부터 안 들어있는 거 아니야? 아, 이걸 빼고. 어떤 거죠? 됐나? 된 것 같은데. 이렇게 해서 다시 포인트 걸로 할까? 안 되네. Okay, I'm gonna fix it after the lunch. So this is a simple breakout game by Atari. And here in this game, we have a simple actions. For example, our action is a simple movement. Right hand side, moving right, moving left, or stay there. So we have 3 actions to take. And what is my objective? My objective is to increase this score. So I know my action, which is simple. I know my objective. And this is actually even much better than the Go game. Just because if I do one action, if I'm successful, then probably the ball will go there and then break one brick. And then immediately you see that a score goes up. So it's much more immediate than the Go game, where the winning outcome comes at the last period. So I would say that this kind of game is a bit simpler. First, in terms of the decision, I have a simple decision like left, right, or in the middle. And also the objective is quite a bit more immediate. So because of that, they can play this game quite well. So by just learning this game for a couple of hours, the machine now becomes an expert, a god of the gamer. Well, and then it can play quite well. So it was quite impressive. So why did they implement this kind of reinforcement learning? They may not develop this reinforcement learning to play the game. So they just apply the same AlphaGo, the algorithm that have played the Go game, then apply it to the, for example, another real application, like the, the data center. Data center is consuming a lot of electricity. So they just apply the deep AlphaGo, and their objective is just reduce the electricity usage as low as possible. So it's an immediate response, and action is not simple, but let's say that their action is just the turning on and turning off some of the machines or computers, servers, or some of the storages and so on. So by just controlling all those configuration, they are trying to reduce the number, the energy consumption, and immediately they have turned on the AlphaGo, machine learning turns on, and then the electricity consumption reduced by more than 40%, which is quite impressive. So it turns out that for any actions whose outcome is observable either immediately or in a short time period, if we can find out the action's result as a reward or objective function, then we are in a good position to play this game very well. And even if the winning or losing probability is quite far from right now, we have a clue because our AlphaGo can play the Go game quite well so far. So, but it needs a lot of hardware at the cost of those efficiency. So what I want to do is maybe we are able to implement this kind of the same method into our inventory problem. But our new spender problem is a little bit too simple. So we don't actually need the reinforcement learning in order to determine the optimal order quantity, because as you see, Excel can do it, right? But for all other problem, probably Excel cannot solve it easily. So because of that, let's extend our simple one-period use vendor problem into a little bit complex multi-period problem. So for multi-period inventory model, we can think of two different structure or setting. The first setting is for each order, we are not paying a fixed ordering cost. And the second case is for a more complex case where we are paying a fixed cost for each ordering time. So you can think of this kind of fixed cost as a delivery cost. So if you are ordering something from Coupang, are you paying some delivery fee? You are not using Coupang anymore? Okay, I understand. Okay. So let's say that you are ordering something from G Market. Yeah, it really depends. And what you love is free delivery cost, 무배, 무료 배송, right? So you can think of the free delivery case as here for the first case, and fixed cost. Sometimes they are charging 2,500 won, 3,000 won. So that's the case of the second part. With delivery cost, without delivery cost. And the specific feature of this delivery cost is this cost does not depend on how many products that you are ordering. It just occurs whenever you order something. So you are paying 3,000 won whenever you're ordering one product, two product, or three product, or four product. Well, you cannot order million product by paying 3,000 won, but let's just exclude those specific case. And we can assume that this kind of cost occurs regardless of your order quantity. Okay, now I want to know what are the optimal inventory order quantity for those two different cases. Obviously, the first one is the simpler one, and the second one is a bit more involved. Okay, in order to calculate it, let's just first introduce some of the necessary measures of this problem. First, I have on-hand inventory, which is the available inventory at the stocking location. In other words, I go to my warehouse and find that I have 100 of my stocks in my warehouse. That's the on-hand inventory. Sometimes I have negative parts in my warehouse. Is it possible? Yes. Sometimes my customer demand is much higher than some products that I have in my warehouse. So my warehouse is empty, but still I have certain customers who are waiting for the parts. Then in that case, I can say that I have some back orders. So my inventory level, that just describe what's going on my warehouse. Either it can have a positive number or negative number. So simply I can say that it's on-hand inventory minus back order. So if a back order is positive, then I will have a minus number. If the on-hand inventory is positive, I will have a plus number here. And obviously, we don't have to think about a situation where both on-hand inventory and back order, both numbers are positive. They never get positive at the same time, which is obvious. The other one that makes this problem more complicated is sometimes we have a lead time. What does that mean? So whenever I order something, it takes a certain time period for me to have it. So that's what we call by lead time. So it takes 1 day or 2 days. or a few hours. Or in the B2B context, it can take up to several months. So because of that, the parts or the products that I ordered today will come a few days later. And at the same time, the products that are coming today is not something that I ordered today. It actually have ordered a few days ago. Okay, so in order to characterize these kind of different structure related to the lead time, I have to have a OO, in other words, on order. So on order is something that are coming that have ordered but not yet have arrived. So because of that, in addition to the inventory level, I need to define inventory position, which includes something that are coming. If we forget about this amount of the inventory of the parts, and if we make our inventory decision not based on this, OO, then we are making a huge mistake, right? So my own order should be incorporated exactly in order to make a timely and an exact inventory decision. So IP is not something that you need to take care in practice, but this is quite important for your inventory decision. Ordering decision. Okay. So based on this, now I want to identify the policy or the rule. But please don't be misunderstood that this is a little bit different from the policy. But this is obviously almost the same as that we have seen in the reinforcement learning or any learning context. So the policy is basically an action rule, right? In other words, if A occurs, my action is B. So it's a structure like that. And I have to identify on which condition A, on which action B should I take. So that's the simple structure of this policy. And as long as I know my rule, I actually have a structure of my policy. So here, a rule can be as simple like that. Every T years or T periods, order a fixed number of products. For example, on every 2 weeks, I want to order 100. So that's a simple application of a policy. I can make it much simpler, much complex. For example, my order amount is your birth year. This can be another simple but stupid order policy. So it's good to know if a certain policy is optimal for a given problem. In other words, no other structure can beat a specific structure like this. So for example, it can be the best structure to order exactly the amount of your birth year. Sometimes this works, but most of the time this doesn't work. In other words, I can find a better structure that can beat A structure. But proving that A structure, A policy, is better than the B policy is not easy because we are talking about the structure of A and B. So in order to make a comparison of A and B structure, I need to implement the best, that best parameter of this structure. In other words, here in every T years, I'm ordering Q, then I have to find out the best T and best Q in my structure. And then I can compare it to another B policy parameter. And then I make the best parameter of B and best parameter of A, and then make a comparison saying that A structure is better than B structure. Or A structure can beat any parameters in B structure. So because of that, it's just a one-time comparison. It involves with a lot of different comparisons, set of comparisons. So because of that, proving that one structure is better than the other is very hard, and sometimes it's impossible. When it is impossible, it means that we don't know which structure is good. If we don't know the structure, then we have no clue about the things, about the basic policy that we want to apply. And then maybe we can numerically just verify all of the different numbers in the problem, which can take a lot of time in some cases. Okay, so the policy, sometimes we can prove the one specific policy is the really optimal for this kind of problem, and at least we have more than 2 results for this kind of optimality of one policy than the other. Why do I take 2 results? Because exactly for this problem, we have 2 settings. So we happen to know that A structure is best for the first setting. B structure is best for the second setting. So that's what we call by base stock policy and SS policy. Probably you may heard about base stock or order up to level, but SS is something new to you. Have you heard about SS policy before? Good. Some of you may not. So let's just verify that, which is a lot harder than just obtaining the one parameter. Or sometimes the other one is also quite difficult, even if you know the best structure. I mean, obtaining the best parameter is not also easy. So we have quite complex problems coming in. So let's just start from the simple one, base stock policy. Here, everything is just the same as our new spender problem, and the only difference is now we have multiple time periods. So in other words, the inventory that I have as a remaining in one period may carry over to the next periods. Also, at the same time, some of the back order that I had in the one time period will also carry over to the next time period. So we have to start from the previous result and then make our own decision of one period, and then it will also impact all the remaining time periods that we have to consider. So obviously, this is quite much more complex than just a one-time decision. But for one-time decision of new spender, we know that the policy structure is order up to S. And how do I find this S, define S? My S is defined by either GS or HS in my proof. And we can anyway find out the optimal order quantity. So it turns out that even for the multiple time period problem, we can extend this result. So how can we extend this result? Let's just go over this part. So we will define the same theta here, but now we have defined a recursive relationship between a t time period and t plus 1 time period. So I have talked to you that in the previous slide that our result of either remaining or any backorder will carry over to t plus 1 time period. So let's just assume theta t of x as the best inventory cost starting from x at t to the end. This is important, to the end. In other words, my theta t is not just the cost of time t period. This is the cost from time t to the end. So summation of all different costs from t and after t. So it's a mixture of many different periods costs. And what I meant by X is something that I already have in my warehouse, okay? before I make my ordering decision of that time period. In other words, this is something I start, and then I can increase it to Y, just as we see from the use vendor analysis. So I can eventually increase my current position X to the Y. So my Y must be, at the same time, just as before, must be greater than or equal to X, because I'm starting from X. So I can only increase it. But if I increase it, this does not come free. So I have to pay purchase cost C of Y minus X for my new purchase. And then I start my problem with Y. And then after obtaining Y, I will realize my demand dt here. And if my demand dt or dt, the random variable, if dt is larger than y, then I will have some shortage. If dt is smaller than y, I will have some remaining. So that's going to be the remaining, or the shortage will be my new starting point of t plus 1 time period. So this is how it works for each one time period to the other. So we're starting from xt and then make our decision to y, and then demand is realized, and depending on the magnitude, that will be my new xt plus 1. So I can define my theta t. This is the cost from t to the end. And then this can be described with my theta t plus 1. And what are the costs difference between theta t plus 1 and theta t? This time period, I will make a decision Y. So my new order quantity would be up to Y position. And if I happen to set my inventory position up to Y, I need to pay this cost. So this cost must be here, right? And depending on my decision, I will have either remaining or some shortage. So the cost coming from either remaining or shortage will go to GY as the use vendor cost function that I have seen before. And all the other thing would go to t plus 1 time period. So any costs that are coming after t plus 1 time period will be included in this one. However, since I'm starting from my y, in the next time period, the position that I will start will be x minus t, y minus t, I'm sorry. So my ending position y minus demand will be my next beginning position. So I have a nice relationship between the two different cost to go function, and the remaining thing is I need to determine the best y here in this multi-period problem. So how to solve this? Yeah, it's a famous dynamic programming formulation. So you have to, in the inventory problems, you should be able to solve a lot of different dynamic programs well. But most of the dynamic programming, the solution is not known. So you will most likely fail to characterize the policy. But for this specific problem, fortunately, we know how to do that. Okay, so let's continue. Probably the end of the time, the last time period, the decision is quite simple. In the last time period, we will have either remaining or we may have some shortage, plus or minus. Let's say that all the remaining will go to the outlet store. And then we can realize a certain cost coming from the remaining. For the shortage, also for the last time period, let's say that all of these customers are going to other store, and then we are losing certain amount of money. So we can realize the cost, either CO or CU. You can define anyway, and we can anyway characterize all the different costs for the last time horizon. What is difficult to take is what are the optimal decision for time t, because I have several other time periods up to the last time period where the game ends, like the AlphaGo, where the go play is finished. So before we go to the T to T, in order to make our best decision at T time period, I need to solve this my theta T, which is coming in this term. But this T plus 1 for the last time period, I will have my theta T definition here, and it will be defined in this way and mix of something, something, and expected function inside of it, I will have T plus 1. But here, that does not have this y minus d random variable anymore because I will not have any new customer demand at the last horizon. At the last horizon, I will just, whatever remaining, I will just recognize the cost based on what I have. So there's no D here, and then I can define this as a many formulation, but the simplest formulation that we can take is maybe for any shortage, I can recognize some cost, and for any remaining, I can sell it as a low price, but anyway, it can be regarded as minus of V because this is cost, and if I can sell it, I can make some money, which is a negative number of the cost. So anyway, I can define this theta t plus 1 as a deterministic function. That's the key point. So I know that, let's just make this theta t plus 1 x as a convex function. I can make it as a convex. Well, because this kind of function just works like this. This is P, T plus 1, this is V, T plus 1, something like that. So it's quite a simple convex function. And because of that, I can assume that we are starting from the convex function. What I want to do is this kind of convexity continues from the backward. So if this is convex, I want to say that theta t is also convex, theta t minus 1 is convex, and then the current time period theta t, I want to make it as a convex function. Why is it important? Because we know that the key part of the news vendor is the convexity of my hy. Because as long as we have a convex function of the cost, then we know that there must be a point, and depending on the x position, my decision is just go up to the s part, right? So I want to implement this result as much as possible. So I can start from theta t plus 1, and then my proof goes like that. So here, so let's assume that this is convex. If theta t plus 1 of x is convex, then obviously theta t plus 1 of x minus k for a constant, this must be also convex. If it's convex, theta t plus 1 of x minus d must be convex, although we have some random variable. So because it's convex, expected value of this is also convex, because the expected value is a combination of probability and the function. So the convexity remains. If this is convex, everything in the middle is just convex. This is convex function. Already we know that. This is a linear function of y. We already know that. So we can claim that this function is also convex. But we gotta be a little bit careful, because we are not just extending this theta into this. We actually have this minimum function here. So let's say that this is my theta t plus 1 x. We are actually taking mean of y greater than or equal to x. So if my x is here, every function value goes to this one here. And then after this one, I will have that. If my x is here, then I will just have this part. So in other words, what I want to say is, even if I start from this shape, the resulting one as by the minimization will be something like that. But still, I can claim that this is convex. Why? Because it's smooth and this is flat, so the convex structure remains. This simple result does not hold for the second setting, unfortunately. Yep. So what I want to say is, still, where is it? 없어졌나? Here, yes. So just like the new spender, the base stock is still optimal for the multi-time period inventory problem. Then it means that each time period, the remaining thing is I need to decide here, ST, here, ST plus 1, and here, ST. So I need to, each time period, I need to decide my base stock level. Unfortunately, so far, my analysis does not tell me how to obtain it. It's just because this comes from the either h function or more complex function and derivative of h function, but it's not easily available and depends on the shape of the setup function. But anyway, I have a clue to obtain it. So, and the best part is I know which structure that I have to implement. So because of that, my problem reduces to find out this simple one parameter instead of trying a lot of different numbers from the beginning to the end. I can easily reduce the problem into one problem optimization, which is a bit easier than this general problem. So we have just done the simple case, and then the remaining, actually no time is remaining. So after lunch, we will see how we can implement the same problem setting with the reinforcement learning. Okay, now we are going into the area, the new approach with the AI-based reinforcement learning. So because of that, we will not talk about this H function and derivative and so on. So instead, let's just focus on solving the dynamic programming as is with this era. Okay, so we will see. So that second part will be based on my it's not recent, it's already a few years ago. So my first paper on the reinforcement learning for the inventory management. Okay, so enjoy your lunch and we will see you again at 2. Thank you.